of them are going into the longitudinal direction. That is because of the nature of the cross section. It is not only kinematics. Then of course you are unlucky. You won't get sufficiently large number of particles having large PT. So isotropy is just that. I mean, you cannot really say it without doing dynamics. Okay? But this is just a qualitative argument to tell you that when a heavy particle decays, most of the final state particles are likely to have large PT, unless your cross section has some peculiarity.
And that means you are talking about resonance events, like when you
No, it has nothing to do with resonance. A heavy particle is produced means it is a resonance production. The cross section of the colliding, the center of mass energy of the colliding particles agree with the mass of the
invariant,
particle.
right?
So in that sense it is always a resonance production. But resonance has nothing to do with the large PT thing. The large PT thing will also depend on the decay properties of the resonance. Okay? And because the decay property, unless there is some very peculiar dynamics, the decay will go all over the place. So you will, but suppose your decay dynamics is pathological, it can produce only longitudinal particles. Then of course this argument falls. But let us not worry about that. The main lesson is when we are searching for new particles, we are searching for particles whose decay is likely to give high PT particles. The invariant mass is not always available. We will see many examples when we can form the invariant mass, but still we can determine the mass. Okay? We will see examples tomorrow perhaps. So the final thing then is we introduce another definition, that is efficiency of a kinematical selection. We have talked about two examples. One is the invariant mass. Now this will have a high efficiency because the background is not likely to have peak at a particular invariant mass, whereas the signal, if it is coming from a new particle produced, is likely to have invariant mass. And PT cut is also likely to have good selection efficiency. So it is basically a percentage. It simply means that if n is the initial number of events, okay, and after the selection you have another number in 1. This may be multiple selection also. You have made multiple kinematical selection in between. At the end of the day you have in 1 number of particles.
So this selection, PT selection is one of the selections.
Yes, I have talked about 2, but there could be 20. Okay. So then the efficiency is defined by 1 by n. So therefore, now on the basis of whatever we discussed so far is
And sir, all the selections are kinematical?
All are kinematics.
All are.
But if you know the dynamics, you can make your selections pointed. For example, I told you that if you already know from the dynamics that particles are going to be produced longitudinally, then you say, oh, forget it. So you have to know everything. You have to know the dynamics, you have to know everything, you have to have some idea of what you are looking for. And that helps you to decide the kinematical selection. So it says that number of signal events will be proportional to cross section. So please note that this is the cross section of the signal process.
Sir, I am in a class, I will give you a call.
Sorry?
Yes. Okay. Professor Parida called me, so I will call him.
Then, so this is like Higgs production. The branching ratio of S means that the particle goes to a particular final state F, and then I write something called epsilon S. This is a number, as you can see here, it is a ratio of numbers. This is called the efficiency. And you have a similar number from the background. Which is the production cross section of the background. What is the branching ratio? That the background produces the same final state. That is important. And then of course this will have a efficiency for the background. Alright. Then of course what you would like to do is make efficiency of the signal as large as possible compared to the background. In that case, even though this number is large, PV bar is produced in a large way. You could select a efficiency in principle. In practice it is impossible, which would give you a reasonable discovery probability of Higgs in the PV bar channel. Well, people are discovering PV bar now, the PV bar channel, although the results are very imprecise. So this is the importance of efficiency, that by choosing the efficiency appropriately, by choosing the efficiency means by choosing the selection cuts appropriately, you can suppress the background compared to the signal as much as possible. So these are the three things. First one is theoretical. You can measure it also experimentally, the cross section. Branching ratio, the same thing. You have to calculate it theoretically. You have to also measure branching ratio experimentally and can match theory and background. And finally this one is also an interplay of theory and background, but this is more experimental. Experimentalists play a more important role in improving the efficiency and the relative number of signal and background.
Sir, we call background because we can't distinguish those from our signal.
So that's what I mean by F.
Right.
F in both cases.
Both cases. But when I am looking at an experiment, I just count number of events of a given time.
No, distribution also.
Distribution also.
What is the particular number
Distribution
of events?
also in particular bean or something. But there I am measuring S plus B because I can't distinguish them, right?
No. You are measuring S plus B, but now in the LHC era, the important thing is you can calculate B. You can of course simulate both S and B. That was what people used to do in the older days. But now you can calculate the background from experiment only. I will come very briefly to it.
Okay, so LHC has collected enough data that it can predict at a given center of mass energy for a given.
Also technique is important. It is not only the number of events.
So it can predict its own background for a given channel very well. So you know the
From
background.
experiment itself.
From the experiment itself.
What kind of signal?
Well, let me give you one example. Although we will be a little late for lunch, but let me give you one example. This is very easy and I have it here. you see here is a continuous distribution. Right? But what you are seeing here is probably S plus B.
Yes.
Because see, background also has some contribution here and the signal gives you a bump.
Bumps. But
Now how do you know the background? The here dependence on theory will be unwise. Simply because this is Higgs discovery, $1 million Nobel Prize question. So what do you do? Since this distribution is continuous, you are sure. What you do is you measure the background here, you measure the background here, and then make an extrapolation technique, which the experimentalists can do very well, I don't know. But extrapolation simply means that you know how to go from here to here. And then you measure the background without any reference to theory. Because you have a curve, continuous curve, by measuring the background, for example, here and here, sufficiently away from the Higgs peak, then by method of extrapolation you go from here to here. Then you know S plus B, you know what B is, and therefore you can measure what signal is.
So is it also possible that if I know that tentatively it is 125 or 26, I did the extrapolation, but also can I have a specific point of the background measured at the experiment at that energy? Then it will validate my extrapolation also that
No, how can you do it?
So it can't be tuned or something.
No, because you will always see Higgs plus background. At that point you will always see Higgs plus background.
Yeah, always it will be little bit here and there.
But the important point is you are not measuring the background on the basis of some theoretical calculation.
Yes. These are experimental data.
That is the new thing. You are determining under this width, under this bump, you are calculating the number of background events from experiment alone. You are not making reference to anything. Alright?
And is there any binning in here also?
Of course, of course.
In N gamma gamma there is a
Of
binning,
course,
right?
of course, of
Which
course.
it is not shown here.
No.
Right.
Now the background here is
Well, the
created by
meaning is
continuous-
shown somewhere here,
It is shown somewhere but not in that plot.
not in that one. But I am sure, yes.
But that extrapolation is done using some fitting curve, right? Using some fitting
Yes,
parameter.
basically that, but I think it is much more sophisticated.
No, it's not the simple extrapolation. You can
It
you
is,
extrapolate
in
from
practice
side,
it
but
is-
you assume actually there is a signal. So you assume you actually bias. So it's not simple extrapolation. Measure the background, the continuous background from different methods, inverting isolations and all kind of stuff. Determine the shape of the background without touching this signal region at all.
In
Because
our
you are
discussion,
completely
Arun,
binded.
if you can tell us more in the discussion, just
Yeah,
one
yeah.
example.
Yes.
It is really
Because
want to know that.
normally we are blinded when you do all this extrapolation. You don't look at that there is a peak or not. If you look at that, then you are completely biased. Then you will see somewhere else and if you bias yourself. So you are doing this without really looking at there is a peak or not in the data. So you don't look at the data point at all when you devise your strategy for background measurement.
But I think this is one of the biggest achievement in physics during the LHC era, that they are now estimating or calculating the background from data only, not from any. Previously it was mostly simulation, that you do a simulation and see how much you
Right.
expect from standard model,
Right.
do a simulation and see how much you expect for a particular signal.
So Monte Carlo.
It was Monte Carlo. But now it is not like that. That is one of the biggest achievement.
But Arun, what did you say? I didn't understand. So you have to tell us. Really take
I
an
think we'll
example.
do it in a discussion.
Right.
We are
Yes,
already
Right.
late.
So sir, we can resume after 1.5 hours. So
we are 2:45.
right. Or say make it 3 then. Should we make it?
3 is fine.
Yeah. So let us resume. So you will resume this discussion, right?
No, I have gone only to the level of proportionality.
So you
Now
will
I would
continue.
write a number
Number.
for this. N